Okay, so let's see. Analysis model reach the object in equilibrium. Let me write it down. So what are the necessary conditions for equilibrium of objects shown in the figure P12.1? Calculate torques about axis through the point O. So now let me redraw the picture. Number one. Oh, hold on. Okay. Number one. And you have the rigid body, the rod, and that's L. And that now the center mass is the middle of the rod, and that have gravity downward. So that Fg is the m times gravitational acceleration constant. That has this rod has also angle with respect to the horizontal axis, theta. And now you apply the force, the tip of rod, and that could be decomposed into the x and y. And now I think the vertical, only vertical force have effective torque on that rod. The rod, so let me see, the middle of this rod, the center of the mass sitting on the middle of this rod, and that is the L over 2. And the number one, gravity at the center of mass. So if you look at the torque from that the gravitational force right on there. So you look at the, let me change the color. Hold on a second. If you look at this torque applied to this spot, then that is gravity, and the radial vector is upward with angle theta. So torque on that spot will be mg, torque on it, then times this is theta, that is r vector. So that is Fg, the gravitational force. The torque itself is the r radial vector cross product F gravitational force. So now now r is the L over 2 times the unit vector in the radial direction, and I assume that the force exerted on this rod is vertical direction, so that make this rod in equilibrium with the gravitational force. So here F, the gravitational force, is mg, y, vertical direction. If you plug these two vector into the torque on the center of mass, then that it should be L over 2 r cross product mg y, and that is mg L over 2 r cross product y. So this two cross product of the unit vector equivalent to mg L over 2 sine. So now let me ask you a question. What's the angle do you think between the radial vector r and the gravitational vector fg?
Isn't it just theta?
So I draw the picture right there. Okay. So now, what's the total angle between the two vectors?
90 plus theta.
Yes. 90 plus theta. Okay. So what's the sign 90 plus theta? Do you know that trigonometric functions with the 90-degree inside of the angle? So like there's like
It's cosine 90 minus theta.
so if the angle is bigger than 90-degree, then this sine 90-degree plus theta should be cosine theta. Okay, 90-degree change the sine to the cosine, cosine to the sine. So that should be cosine theta. So that should be mg L over 2 cosine theta. Now let's just change the focus to the external force. So as I said, in order to stay in balance, stay in equilibrium, you have to apply the external force at the tip of this rod right there. So number 2, external force. So now you have force applied to, that's what I assume, Fy, in order to stay in equilibrium, that Fy applied to the end of this rod that has distance L from the rotational spot, theta. So that is L. So you can think of this as Fy, and that is radial vector, R, and that is external force. And this is what this angle, what angle do you think that is between this R vector and the Fy, external force? This is external force. Okay, what is the angle do you think between this radial vector of a rod and the vertical external force?
Cosine theta.
No, I'm asking that what is this angle? Can you guess what that angle would be? So now this is the angle between the horizontal line and this rod is theta, right? So the vertical direction, the angle between this vertical line and this radial vector would be what? This is total angle between horizontal line and the vertical line is 90 degree, right? And you got to take that theta out of it. So that is the 90 degree minus theta, right? So if you plug that into this formula, then that torque, external torque, is R cross product F(ext), and now you have to add R vector with the L times R radial vector. Same thing for F external force is Fy and the Y fraction. So now Fy, you plug that into this formula in the torque, that should be L R unit vector cross product Fy Y. So that is L Fy R vertical for L Y. So that is what? Sine Okay, 90 degree minus theta. So what is this? Sine 90 minus theta is, can you express with a different trigonometric function? What is that? Sine 90 degree minus theta is, do you remember? This one is what? Sine 90 degree minus theta.
I don't remember.
So that is 90 degree inside of the sine of trigonometric function. As I said, that's just the sine function could be converted to the cosine function. Cosine function could be converted to the sine function. So like there's like, so that is the L F Y cosine theta. So in the case if you have like a vertical force, then that is net torque from the external force. Okay, so now in order to stay in the the system in equilibrium, the external force, external force, and the torque from the external force should be same as the one from this rod. So that is F Y L cosine theta, the same as the other, that gravitation, the torque from the gravity right there. So that should be same as this one. F Z L over 2 and cosine theta. Let's cancel out the cosine theta out of it, and just L is canceled out. So the Fy is the mg over 2. You split that gravity into the Fy direction. So you can do the same thing for the case that the force actually exerted in horizontal direction too, Fx. So in the case you have the force applied to the Fx, then the same thing, but you have the external force. Gravitational force part is the same, but you have the radial vector this direction, L, R, and external force this direction. I'm sorry, that X, Fx. So that is the torque, external torque out of the force in horizontal direction is L, R, cross product, F, X, L, X here. So if you do that, then it's L, F, X. Oh, this one is actually not FL. This one. So that is FXL times R cross product X. This one is sine theta. So net external torque is FXL sine theta. So if you have the horizontal external force applied to the end of the rod, then that torque should be same as the torque from the gravity. So that was mgl2 cosine theta. So from that, Fx should be mgl over L sine theta cosine theta. So the L is cancel out from numerator and denominator. That's lead to the mg to cotangent theta. Okay, so that depends on which direction that the external force applied to the end of the rod. That could be half of the gravity, or that the depend on the angle of this rod. Okay, so if you apply the gravitational force, I mean the external force to the end of the rod in vertical direction, only need half of that gravity to the compensate the weight of this rod. But if you have external force original direction, the amount of force applied to keep the system in equilibrium, it depends on the angle of rod. Okay, so that is the number one. And let's take a look at the number two. So number two. Oh, that's I gotta take the picture of that at the end. So let me grab it. No home. No, snapshot. All right. Right there. Okay, good. Okay. Let me take a snapshot of this one and copy into the slides. Okay, and let me switch to presentation mode. So number two, why is the following situation impossible? A uniform beam of a mass mb, 3 kilogram, and the length L is 1 meter support blocks with the masses m1 5 kilogram and m2 is 15 kilogram at the two positions as shown in the figure 12.2. The beam rests on the two triangle blocks with the point P, a distance d 0.3 meter to the right of the center of gravity of the beam. So the position of the object of mass m2 is adjusted along the length of the beam until normal force on the beam at O is 0. So what is the problem? What question of this problem? I don't see that actually question itself.
It's asking why is the following situation possible?
Are you sure that that's the question? That is actually just meaning of this problem, but let me take a look at. Let's see. So there's no other, actually, the question with this problem?
Oh,
Is that's question only you see from
yeah.
Is that right?
Yeah, that was the only thing on the textbook.
Okay. Well, then, let me, okay. So now, let me, I just explain the situation. I think, now you have this, beam, right? And the middle of this beam is center of gravity, downward. And, you have two masses. One, M1 is the end of this beam, and M2, there's another, actually, triangle supporting this rod. There's two triangle, right? And just supporting this beam. And M2 is sitting on the other side of this beam. Okay, so the two masses sitting there. So first of all, I think you should actually just estimate the net torque out of this M1 and M2. And you have to just estimate the torque out of two masses and find out the x value. Estimate x out of that condition. So total net torque based on this one, point P is the rotational axis. So like basically, I was not quite sure that what is the question means, if that is a real question. So it said this following situation impossible, then it depends on the x value, right? So why is that the situation would be the impossible? I mean, depend on this x value. The beam is now, it is not on the balance, it's not in the equilibrium. That's what the question actually means. So that beam is not staying in the equilibrium, and so that's one side actually moving the other side, or just kind of rotate. So it's not stationary. That's this question means. Or doesn't matter what kind of mass or what kind of value you have, this one will not be in the equilibrium. That's what this question means. If there's no additional question attached to this problem.
Okay.
So I was not sure that actually what this question actually just solve actually. So let me just explain what I understood from this question, and then maybe we can find out what that means. Okay, so net torque between these two masses. If you consider that point P is the rotational spot, then depend on the mass M2 and depend on this x of the distance from the pivot point to this mass M2. I thought that's M2 possibly just M1. I mean, M2 possibly just raise the M1 so that point O is going to be separated from this triangle. So that was my assumption. So if that is case, this net torque and the left-hand side of point P could be combination of the torque out of M1, torque out of the gravity, center of gravity. based on the distance, this rotational axis. So you have down force from mass 1, okay, also force downwards from the center of gravity. So that torque on the left-hand side out of this, the point P is delta L1 plus delta L2. And now, because this two forces in the left-hand side downwards, but their radial vector is this direction. So that is opposite to this torque. That is actually force is downward out of M2, but their radial vector is this direction. It's gravity 1, that is gravity CZ. So assuming you have the force in downward and left-hand side, but the radial vector is toward the left-hand side, their torque of this, the one in the left-hand side of this rotational force is out of this whiteboard. But the torque produced by the force out of the M2, the radial vector is this direction. The force out of gravity is downward. So the torque, direction of the torque is inward the whiteboard. So you gotta just, if you decide the stand in outward, the whiteboard is positive direction, then the torque, inward, the whiteboard should be minus the direction. So that should be torque R. So if you plug that, the definition of the torque out of a given parameter, that is R L1 times FL1 plus RL2 FL2 minus R2 FR. So here's RL1 and RL2 is basically distance from the rotational center P. So the RL1 is L over 2 plus D, and the FL1 should be the mass of the weight of the M1 mass M1, and RL2 should be D. L2 is let me just clear up. Let me just show you the variables of this one. So basically, this one is RL2, and from here to here is RL1, and the X itself is R and R of right hand side, the distance. So that is FL2 is MB is G. So that is the weight of this beam, which is the center of mass, and R is X, the distance from the rotation center to the M2, and FR is M2 Z. So you plug them all into this formula, then that should be M2Z X is M1Z L over 2 plus D plus M B, Z, D. So I thought if this torque on the left-hand side is bigger than the one, the right-hand side. So let me just look back. So that the torque out of this M2 is bigger than torque from the ones in the left-hand side, then this beam will be lift that M1 out of the point O. That was my understanding. So in order to do that, this X value, let me just show you this, the equation, left-hand side should be bigger than right-hand side. In that case, M2 push the M1 up, and that's M1, the beam can be detached out of the point O. That's my thought out of this problem. So if you just divide the both sides of this equation, then G out of this formula, then you can just move the M2 to the left-hand side, and X should be M1. Okay, 1 of M2 divided by, multiply by M1 times D plus L over 2 plus M B D. So now you plug that numbers in. If you take a look at the problem, then MB is 3 kilogram, L is 1 meter, and M1 is 5 kilogram, and M2 is 15 kilogram, and D is 0.3 meter. So if you plug those numbers into this result, then that should be 1 over 15, the M2 is 15, right? Times 5 times 0.3 plus 1 of 2 plus 3 times 0.3. So from that, this one seems like it's 0.3, about 0.2667 meter, which is about 0.327 meter. Okay, so if the X is larger than this number, then basically that could lift up this M up out of this O, if I understood correctly this problem. Okay, so that's create that make that this beams out of the equilibrium, and because that make this M1 is upward with the larger size, the distance, more distance out of it. So this M2 is 0.327 meter or bigger, then that's supposed to actually push the M1 up, based on what I read from this problem. Okay. That's the two problems out of the section 12.1. So what else do you want to just go through after this? Let me look back. Any problems before this or after this? I can't hear you.
Just after. The ones after.
Okay.
The ones I circled, yeah.
Okay, so let's take a look at number 10 then. Okay, number 10. All right, let me take a picture of it.
So the room is closing in 10 seconds, I think.
Oh, 10 seconds? Okay, let's wait for 10 seconds then.
Okay.